Welcome to 16.2, Part 2, which I've entitled Colors. What we're going to talk about in this section is how do you combine things to get color, both paint and light, because they're different. When you pull open your cell phone and the computer screen that you're watching this on right now, it's using the fact that your eyes perceive light at different wavelengths to trick your brain into seeing colors. How does it do that? How do we see color? How do I make different colors with my computer screen? That's what we're going to be talking about today. And to get us started, there's a couple of videos I wanted to show you. First, there's this one from a TED Talk that I noticed a little while ago.
Enough about bobbing corks. What about light and color? If light is a wave, then it must have a frequency, right? Well, yes, it does, and it turns out that we already have a name for the frequency of the light.
This is kind of an intro, just a general introduction. You know all this already.
Color is nothing more than a measure of how quickly the light waves are waving. If our eyes were quick enough, we might be able to observe this periodic motion directly, like we can with the cork in the ocean. But the frequency of the light we see is so high, it waves up and down over 400 million times a second, that we can't possibly see it as a wave. But we can tell, by looking at its color, what its frequency is. The lowest frequency light that we can see is red, and the highest frequency is purple. In between, all the other frequencies form a continuous band of color called the visible spectrum. So, what if you had a yellow pencil sitting on your desk? Well, the sun emits all colors of light, so light of all colors is hitting your pencil. The pencil looks yellow because it reflects yellow light more than it reflects the other colors. What happens to the blue, purple, and red light? They get absorbed, and the energy they're carrying gets turned into heat. It's similar with objects of other colors. Blue things reflect blue light, red things reflect red light, and so on. White objects reflect
that's really important. The reason that you see a yellow pencil is because it's reflecting yellow light into your eyes. And you see blue reflects blue. It absorbs everything else except the color that it seems to us.
All colors of light, while black things do exactly the opposite and absorb at all frequencies. This, by the way, is why it's uncomfortable to wear your favorite Metallica t-shirt on a sunny day.
Now, we're going to get a little bit more into it here. We go by what's called the RGB color spectrum. The RGB, and you'll see here red, green, and blue. Maybe you've seen this if you played around with your computer's color preferences, or you get into Microsoft Paint or into Photoshop, you start seeing the RGB, and you'll also see something called CMYK. And we're going to explain both of those today. So here's how RGB works. He does a really great example of, he does a really good job of showing
Purple is a weird color. The formal name for purple is magenta. And the weird thing about magenta is that you won't ever see it in a rainbow. And the rainbow is supposed to be the full spectrum of colors. So why doesn't magenta appear in the rainbow? And the answer is to do with color mixing. I've always had a problem with color mixing because I know that you can't mix photons together. So you can't take a blue photon and a green photon and mix them together to get some other photon. That just doesn't happen. And yet you can mix paints together in art. Like, color mixing is definitely something you can do. So what's the answer? Well, actually, you can't mix colors together in physics, but you can do it in biology. It's to do with how your eyes work. For example, if I shine red light and green light into your eyes at the same time, if I cross these over, you will see yellow. So when you mix red and green together, you get yellow. And if you look at the spectrum, yellow is in between red and green. So maybe that's the rule for mixing colors together. You mix two colors together, you get the color in between on the color spectrum. And we can test that again. So I'll look at green and blue together. So if I mix green and blue together, I get cyan. And cyan is in between blue and green on the spectrum. So that's great. You mix two colors together, you get the color in between. But why? Why is that? Well, your eyes can't measure the wavelength of light directly. So it's not like a photon comes in and it's, 200 nanometers or whatever, and it detects that. Instead, you have these cone cells at the back of your eyes that are sensitive to different parts of the spectrum. So when red light comes into your eyes, there's a set of cones that fire and tell your brain you're looking at something red. So we'd call those the red cones. There's another set of cones that are more sensitive to green. So when there's green light going into your eyes, they fire and they send a message to your brain. And there's blue cones as well. So you've got red cones, green cones, and blue cones. So what about yellow? What about when you're looking at yellow light like that? Well, in that situation, you don't have a yellow cone. So what do? Well, yellow is quite close to red, so your red cone fires a bit. And yellow is quite close to green as well, so your green cone fires a bit. So your brain is getting a message from your red cone and your green cone at the same time, and it's deciding, okay, well, I must be looking at something in between those two colours then. And that's brilliant, because your brain is perceiving something about the world that it isn't able to measure directly. It isn't directly sensitive to yellow light. It does mean that you can be tricked. And so if I make red light and green light go into your eyes, but no yellow light, you will see yellow anyway. So I've got a red torch and a green torch, and there's no yellow light here. But when I combine them, you will see yellow.
Believe it or not, this is exactly what your computer's doing. If you were to zoom in on your pixels right now, on your TV, on this computer screen, if you looked at the yellow that's there, it's going to be the red and the green are going to be lit up. And then they're shining it into your eyes, and you perceive that as yellow.
Anyway. And TVs do this all the time. So if you look up close at a TV, you'll see the individual pixels, and there are red pixels.
And you can see, look at this pixel right here. A lot of these pixels are turned off, and that's how we get black. Black is the absence of light. And in here, how do we get a white number? Well, you shine red, green, and blue together, and that gives you white. Well, this number right here, see how you get blue and green? So this is going to be cyan. See, this pixel, the red, is turned off. So here's going to be a cyan pixel. So they just vary the different colors. I think you'll talk about this a little more.
Green pixels and blue pixels. Those are the only colors being produced by your TV. And yet, they can produce all the other colors with this trick of color mixing. So what about purple? What about magenta? Well, what should your brain do if your red cone fires at one end of the spectrum and your blue cone fires at the other end of the spectrum, but your green cone doesn't fire? Does it do the same trick? Does it think, I must be looking at a colour in between red and blue? Well, the colour in between red and blue is green, and you're definitely not looking at something green because your green cone isn't firing. So in that situation, your brain invents a colour. It makes up a colour, and that colour is magenta. And I can show you that. So with my red and blue torches, so when they combine together, there you see magenta. Absolutely beautiful. And that's why you don't see magenta in the spectrum. You don't see magenta in the rainbow, because it doesn't have a wavelength. It's just the absence of green, if you like. Just to show you the full palette of colours that you can see on a TV screen. So you get red and blue mixed together makes magenta. Green and red makes yellow. Green and blue makes cyan. When you mix them all together, you get white. So when your red cone, your green cone, and your blue cone are firing together, you get white light.
And your television is taking advantage of that biological fact in the back of your eye, that there's a cone for red, a cone for blue, and a cone for green. So it's got a red, blue, and green light in there, and it just varies the intensity of each to make all the colors of the rainbow. And there's something like, well, your pixels on your TV screen, on your computer screen, your iPod screen, your phone screens, they can go, if you turn them all the way off, they assign that 0. If you turn them all the way on, they assign that 255. So there's actually 256 separate settings. So each of the three has 256. So there's literally 16 million different iterations and permutations of those three settings. So you can get 16 million different colors on each pixel if you'd like. And your eye can't really perceive that many colors, but it's the computer screen is able to do that. So let's kind of reiterate what he just said. Colors by addition. So what you've got, when you combine blue light and green light, you notice what happened. So blue light plus green light is going to equal cyan. And then green light plus red light is going to be equal to yellow. And if you take blue and you take red, you get magenta. All three of them together gives you white. So this is what's called colors by addition. You're adding light together. The primary colors are red, green, and blue. So these are the primary colors of light. Now this is different than art class. The primary colors in art and paint were, I think, green, red, and yellow, or red, blue, yellow, I think, are the primary colors of light. This has nothing to do with art class. This is not art. This is physics. The primary colors are red, green, blue, and the secondary colors are cyan, magenta, and yellow. So complementary colors. Complementary colors are if you add two of them to get white. For instance, let me show you something. Like what if I took yellow and I added blue to it? What is that going to equal? Well, you know that yellow is both red and green together. So what yellow really is red and green. And then when you add blue to the whole mix, you end up with red plus green plus blue equals white. So these complementary colors, blue and yellow, notice where they are on the color wheel. Another set of complementary colors are going to be green and magenta, red and cyan. They're exactly opposite one another. Those two you're going to add to make different colors. Now, I've got a little program that I can use to kind of simulate how a computer works. I found this program, a few friends of mine that are physics teachers came up with this. And what it is I can control each of the pixels on my computer. So I can turn them all the way on to 25, turn this one all the way on to 25, turn this one all the way on. So if I have red, green, and blue, I can make white down here in the field. So to make red, what I would do is I'd turn off the green one and I turn off the blue one and I make red. So let's make blue. Well, let's make dark blue. So in order to get blue, I have to turn the blue pixel on, and I'll turn the red pixel. So I've got blue. But how do I make blue darker? How does my laptop make a dark blue? Well, you have to add black to it, meaning that I have to turn this down. So I turn this down, and there I've got my dark blue. If I turn it all the way off, I get all the pixels off. That's what black is. So how do I make something like light blue? So if I turn my blue all the way on, I get blue, but now I have to add white to it. In order to add white to it, I have to add a little bit of red and green, because red, green, and blue make white. So what I do is I add a little bit of, let's go 14 and 14. That's a little bit, I'm colorblind, by the way. It looks a little bit too dark, so I'm going to make it a little bit whiter. So I have to add more of each of these to it. So maybe I go 19 and 19. That's too white, so then I can go back down to maybe 16 and 16. I'm getting pretty close. But that's how you make things, whiter. For instance, let's go to yellow. I wonder or orange. I make orange by doing red, because red and green together, red and green are going to make yellow. But I want to make it darker, because orange is darker yellow. So I'm going to turn these down. That's how I make it darker. So I'll turn this down to 17, maybe turn this down to 17. That looks like it's a little bit too far. Maybe I want to go a little higher, 22 and 22. Maybe I want to add a little bit of this to it. Let's dark deepen this, 17 and 17. Maybe a little bit more. Well, I'm not so good at this. Well, we'll play around with this in class. The next thing I want to talk about are pigments. Colors by subtraction. And I think a good way to do this is to show you this picture right here. This is a picture that I took out of your book. It's 5 different colored dice. A red one, a yellow one, a white, a green, and a blue. Now, like you said before, the reason that we see red is that we've got white light, we've got red. You can think of white as red, green, and blue. And then what red does is red will reflect the red, but then it will absorb the green and it will absorb the blue. They stop. So that's why we see red light. And the white one, I take those same red, green, and blue, and that's going to reflect all of them, red and green and blue. And then I take that white light on here, and it's going to reflect the blue, absorb the green, and the red. Now, the absorption is really important because, like we said here, this absorbs red and this absorbs green, and it reflects blue. That's why you see blue. Now, and if you only shine red light, which is this second picture, I'm shining red light on a blue dice, what it's going to do is it's going to absorb that red light and reflect nothing. And when it reflects nothing, that's what black is. That's why this dice looks black, is because the red light that's being shined upon it is absorbed. Same with the green dice. Going back over here, the green absorbs the red. So it's going to, and it's also going to absorb the blue. It will reflect green. So when I take red light and I shine it on a green dice like this, it absorbs that and reflects nothing. When it reflects nothing, that is black. Go back over here to red. We know that red reflects red, and that's why this one looks red. This yellow, remember how we see yellow? Yellow is both red and green together. That's why we see yellow, because if you're here, red light and green light are going into your eyes, and in this second picture here, if you shine red light on it, it reflects red, and that red is going to go into your eyes. That's why this looks red, and this looks red. Because white reflects everything, yellow is going to reflect both red and green, and red is going to only reflect red. Now, take that same school of thought and go over here to the blue. I've got blue light coming in. It's striking a red die, and we know that red absorbs blue, so it absorbs nothing. It absorbs everything here and reflects nothing, and that's why it looks black. That's why sometimes we talk about pigments as color by subtraction. That light is landing on it and it's being subtracted. Like this black shirt that you're seeing, all the light is absorbed and nothing is reflected. The red in my Hillman, it's absorbing the blue and absorbing the green and reflecting the red. So substances that absorb and they subtract certain colors, those are called pigments and dyes. So the primary pigments, now this is different. The primary pigments are cyan, magenta, and yellow. It's exactly opposite from the light colors. And the secondary pigments are red, green, and blue. So what you're going to do, how do we make blue? Like if you've ever looked inside your printer, if you have a color printer at home, there's a cyan, magenta, yellow, and black cartridge. You can make every color in the whole rainbow only using cyan, magenta, yellow, and black. So how do I make blue? So what I'm going to do to make blue is I'm going to combine cyan and magenta. Because cyan plus magenta, you know that cyan, in order for your eyes to see cyan, it has to give you blue and green. So cyan absorbs red. It reflects blue and green. Magenta, the same thing. Magenta over here, magenta, in order to see magenta, you have to be seeing blue and you have to be seeing red. So it absorbs green. Which means it reflects blue and red. Now think about this. If you're taking something that absorbs red and you're taking something that absorbs green, so here's your puddle of something, and you've got white light, which you can red, green, and blue, and what it does, it's absorbing red, so you're absorbing the red, and you're absorbing the green, what's going to reflect away from it? Blue. This is why we call this colors by subtraction, because we're subtracting away the red, we're subtracting away the green, and that's how we end up getting blue. So if you wanted to make all the rest of the colors, like if you wanted to make red, you would combine magenta and yellow. If you wanted to make green, you would combine cyan and yellow. If you wanted to make blue, cyan, and magenta. Now, how do you make white? You cannot do that. You can't make white combining, just like with color, with light, if we combine all the colors of light, we end up getting white. But if we combine all the colors of pigment, we get black. Adding things together that absorb everything else, that's going to give you black. So the only way to make white is you just, no color. You envision yourself with a white piece of paper, no paint equals white. And it's the exact opposite for light. Like, no light equals black. All colors of light equal white. All colors of paint equal black. No colors of paint equal white. They're completely different. Combining colors and combining light. So it's a little bit confusing. We're going to discuss it a little bit more in class, but that's the gist. The primary pigments, the secondary pigments, the primary colors of light, the secondary colors of light. How does your iPhone screen work? How do we make colors?